Yes, and use this YouTube. YouTube. And this one go so no, it's not made for keep. And application. Save. And to copy from this here. Okay. Copy that to this. Save. Yes, so I'm now gonna see the YouTube and YouTube. This language. Studio. This one. No, you have to log into these one, right? So no to add sign on. Oh my god. It's long count. To studio. And this one fully on. Reset. Copy. Stellen. Stellen. This one. Start. And everyone is there. And this.
Okay.
SK. And this one. Here. Okay, good afternoon, everybody. Welcome you to SCI33205. I hope that everything is fine. All right. Okay, we go to our lecture notes, right? It's taught therein. And
today, many of you, especially the students from M605, has spent time, needs to spend time in a hospital at Lama Tibadi Hospital. I don't know for what purpose, but it's a good thing that you just, okay. As usual, you just type your name, okay, in the chat box so that we could recognize each other that you appear here in the, like that, okay. So that we can recognize that you appear in the classroom, right? What I forget to mention, okay. Okay, let's go ahead with our story. This is for M604, right? You have already seen some detail, right, of the creating. You have already seen some application of the have you seen this already, right? The, I don't know, last time we arrived at ถึงตรงไหนครับมีคนไหนจำได้ไหมนะครับกลับไปกับเดี๋ยวผมขอเปิด604 right no but not this one อันนี้ขออนุญาตไม่ใช่ไฟล์นี้เพราะว่าผมดันไปแอดงานวิจัยใส่ตรงนี้นะครับกดผิดนะครับมันแอดมานะครับน่าจะถึงตรงนี้นะครับที่นี่นะultraviolet okay 5 ultraviolet okay we arrive here and yeah that's the unit wavelength, right? It's the wavelength for the ultraviolet. I'm not sure whether okay พระนะใช่นะครับ okay พระนะใช่ where is the mouse okay here พระนะใช่ okay we arrive at the ultraviolet, right, which is the frequency band below the, I think, over, okay, above the typical visible light for us that the human eyes can detect, right? What is the reason why I say it's the band above the typical light? Because the frequency band is higher here, okay, because you have shorter wavelength. Shorter wavelength means you have higher frequency. Okay, that's why we say it's the frequency band above the visible light, and the wavelength, okay, is given from 0.6 nanometer until 400 nanometer. And what is the source of this visible light? Oh no. No. ชัยกฤษนะครับชัยกฤษโปรดดูที่รายกลุ่มนะชัยกฤษสอบของมสวนะครับของ EE 111นะครับเข้าอีกกลุ่มหนึ่งนะครับคุณดูที่รายกลุ่มนะชัยกฤษออกไปนะครับอันนี้มันเป็นของม.ปลายนะครับokay this is the sun, right? The sun, which is the source of the ultraviolet light. And yes, and the ultraviolet is the cause of suntans, okay, that will burn our skin. All right. And most of the UV lights come from the sun, and our skin and the atoms in many living creation, not only human, we absorb the ultraviolet. Okay, in some of the ultraviolet will be also absorbed in the upper atmosphere, and the name of that upper atmosphere is called stratosphere. In the stratosphere, the ozone is generated by ultraviolet light, and it's the reaction between oxygen and ultraviolet radiation. Ultraviolet is used for human on Earth in the sterilization, okay, in order to keep some milk to stay longer, to last longer, and it's used also for vitamin D production to human body. And unfortunately, the ultraviolet light is a cause of cancer. And now we arrive at almost the last type of the frequency band by electromagnetic waves. For those of you who want to attain or who want to be on leave, because you need to attain the the special duty, okay, so that you can apply for the doctor education program at some university. Just leave me the letter of leave or photo of leave. Okay, when you are there, just take a photo and send me by email or by line. Okay, but it may not happen with you in M604. Most of them are in M605. Okay. Now let's talk about X-ray. X-ray is maybe quite familiar to us, because you may have ever heard the word X-ray when you go to the hospital to see something in your chest, right? Okay. Yes, X-ray has the wavelength from 10 to negative 19 meter, or in terms of appropriate scale, it's called 0.1 picometer. You know, pico is 10 to negative 12, right? And you have one additional negative 1. You have an additional negative 1 here. To the longer, the maximum length, which is 10 to negative 8, it's called 10 nanometer. The most common source of the X-ray is, it can be is generated by human also. It can be the acceleration of high energy electrons. Okay, that is the electron is generated, is accelerated, and it hits a metal target. And in terms of nuclear physics, it's called a bombardment or bombarding, like this. Okay, X-ray easily penetrate or damage, destroy living tissues or organisms. We use this for special purpose. Your body is not allowed to receive X-ray for a long time. Okay, only a certain time, and after that you need some time to recover your body. And if you want to make X-ray later, you need to take rest. Okay. It is used as a diagnostic tool in medicine, and yeah, the good thing. Okay, it is also one of the treatment for certain form of cancer. And now let's talk about the most dangerous type of the electromagnetic wave. It has the highest amount of energy. I'm not sure whether you can hear me well or not. เสียงได้ยินนะครับที่ซูมนะครับ yeah, it's called gamma rays. Okay, you may see or know later that gamma ray is caused by the nucleus of several isotopes, several unstable isotopes. So once they cool them down, okay, to have the stable state, they are gonna release those nuclei will release the gamma rays, okay, which is a kind of photon, but it's the photon with a very, very high amount of energy. Okay, what about the wavelength? Wavelength of gamma ray is from 10 to -14 to 10, or in spatial scale, you know, this is femtometer. Maybe I have already explained it to you. It's 10 to -15, sorry, 10 to -15, and once we have 10 of that, it's going to be 10 to -14. Okay, this one is called femtometer or Fermi. And after that, we have 10 to that the maximum length, right? Maximum length of the wavelength, it's 10 to -10, or it's 0.1 nanometer, okay, which is very, very small, less than the visible light. Okay, yeah, as I mentioned it's the gamma rays are emitted by radioactive nuclei. Okay, nuclei is the plural word of nucleus นะครับก็คือรังสีแกมมานะครับถูกสร้างขึ้นมาจากการลดเขาเรียกว่าอะไรลดการสั่นไหวลดคือนิวเคลียสนะครับพอเขามีปริมาณมากๆแล้วนะครับพอมีขนาดใหญ่นะครับเขาจะลดขนาดนะครับเนื่องจากว่ามันไม่เสถียรนะครับมีอัตราส่วนโปรตอนหรือว่านิวตรอนที่ใหญ่ไปอย่างเงี้ยนะครับมีอัตราส่วนโปรตอนนิวตรอนที่ไม่เหมาะสมอย่างเงี้ยนะครับธรรมชาติก็จะทำให้นิวเคลียสนั้นนะครับลดขนาดลงก็คือแตกออกมานะครับพอแตกออกมาแล้วนะครับก็จะมีปล่อยรังสีเนาะรังสีก็ได้แก่พวกอัลฟาเบต้านะครับอัลฟาก็เป็นนิวเคลียสของฮีเลียม42นะครับแล้วก็เบต้าก็จะเป็นพวกอิเล็กตรอนหรือว่าโพซิตรอนนะครับแต่ว่าเมื่อลดขนาดตัวเองลงมาแล้วนะครับก็ยังไม่เพียงพอนะครับในบางครั้งนะครับเขาก็จะเรียกว่านิวเคลียสที่แตกออกมาแล้วนั้นนะครับก็ยังมีการสั่นไหวอยู่นะครับก็จะลดพลังงานตัวเองครับเพื่อให้หยุดการสั่นไหวเนาะเพราะว่าตัวเหมือนกับเรายังร้อนอยู่นะครับยังร้อนรุ่มอยู่ก็จะสั่นไหวนะครับเพราะเพื่อให้ลดการสั่นไหวนะครับเขาก็จะปล่อยพลังงานออกมานะครับเพื่อให้ตัวเองอยู่นิ่งพลังงานแบบนั้นนะครับเราเรียกว่าเป็นรังสีแสงคือโฟตอนนี่แหละนะครับแต่ว่ามีพลังงานสูงมากนะครับสูงมากเราก็จะเรียกว่าเป็นแกมมาเรย์นะครับดังที่เราเรียนในเรื่องนี้นะครับ okay and that's the reason why we have the gamma ray. Yeah, as I told you, it's a very dangerous ray. Actually, it can penetrate very well and cause serious damage to human tissue when our living creature tissue absorb them. Okay, it's dangerous. Yeah. What about the next aspect? In gamma rays, if you work somewhere there, okay, if you work somewhere close to the source of the gamma ray, you have to wear a spatial protection cloth, okay, but I don't think it's possible because to be safe, you need to wear the cloth which should be made of lead, you know, PB leads, and in the scale of several inches. It's impossible actually. Okay, the normal clothes would not be appropriate for us to would not be sufficient for us to protect the gamma rays. All right. Okay. Now let's talk about the next thing. You have to wear the clothes by garment that can heavily absorb the gamma rays. For example, several layers of lead. I think it's very difficult to have such clothes. And ถ้าไม่มีใครเข้าอีกแล้วขออนุญาตปิดซูมนะครับ Okay. Okay. Let me upload the problem to exam for the bachelor degree. Okay. What about the good thing? What is the benefit of the gamma rays? It is used for nuclear medicine. Okay, and it's used also for security purpose. It's used also for medical diagnosis and to cure some types of cancer. We use also the gamma rays, and there is also there are also other application from gamma rays. But if you absorb the gamma rays accidentally, you may get cancer easily. Okay, that's the bad thing. As the wavelength reduces, as you can see before, when the wavelength reduces, the energy of the emitted wave increases, right? When the frequency band is higher, you get a higher amount of energy. And if you go to chapter 6, okay, there is a formula which is called Planck constant. It's equal to E equal to HF. Okay, so when the frequency is greater, you get more energy. Okay, but we will not talk about that in this chapter. All right. Now let's talk about the big scale of the electromagnetic frequency band. All right. Here you have several kinds of application, right? As we have seen in the text, and you can see the wavelength from the highest amount, okay, the greatest amount of wavelength, to the shorter and shorter and shortest at the gamma rays region. All right. Okay. นะครับระหว่างที่ผมสอนนะครับเพื่อนรุ่นพี่ขอสอบเวลานี้ด้วยนะผมก็ต้องมอนิเตอร์เขาอีกเครื่องนึงนะครับแต่ไม่เกี่ยวกับคุณนะครับคุณเราก็เรียนของเราไปนะครับ Okay. This is called extremely low frequency band. Okay, there could be many names of bands in electromagnetic wave. This is called extremely low frequency. It has spatial feature. It's safe. It's beneficial. If you receive it in appropriate dosage, okay, it's still safe for us because you know the reason why, because it has low energy. But if you go further, when the wavelength is decreased, okay, when the wavelength decreases, we have a little bit higher amount of energy. It's called very low frequency region. Okay, here you can see this amount, this electromagnetic wave. It can be emitted from the electrical socket, okay, at your home, and there will be also some electromagnetic wave induced from the transmission lines on the transmission tower. For example, in Thailand, we have these such kind of towers next to the road, right? On the road, we once along the road, we have the tower. And yeah, you can get the very low frequency electromagnetic wave from this tower. And let's move to a little bit to the right. You can see that the length of the wave is shorter and is known as low frequency band, okay, low frequency region. Human uses this band for the purpose of television and radio in several kinds of broadcast television. What about the dangerous? What about the dangerous stage? It's almost safe, okay, low danger. If you stay close to the television tower, you would receive something which is not very harmful to you, okay? And once we go further to the right, the wavelength is shorter, okay, compared to the original, the beginning one. Human uses this band for radio transmission, for wireless communication, and it starts to be a little bit dangerous, okay, if you stay in that place in a very, very long period. Yeah, once we move further, we are gonna reach the microwave region, and human use this band for the purpose of wireless communication, like your smartphone, your handy, your mobile phone. And in order to, this is used for communication, right? For talking, for sending the message, for transferring some information that you want to send, right? But in another sense, if you really want to get the heat or the energy, human design that device, which is known as microwave oven, okay? But still, these devices use the same band, frequency band, as the one in wireless communication, but for spatial purpose, they're gonna transmit very, very high amount of energy in this microwave oven. And if you go further, it's called, it's gonna be the band for satellite communication, which is a kind of long transmission system. If we go further, it's going to be called infrared, right? We use this for television remote control or something like that, and it's going to bring you some heat, okay, with this one. And once we go further, as you know, the wavelength is going to be shorter and shorter, and we reach the visible range of the light. Okay, it's generated mainly from the sun, by the sun. And if you go further, okay, let's talk about the danger from this one. It's still safe and beneficial in appropriate dosage. Okay, if you spend time in the morning, you can improve your body because you can get vitamin D, okay, from the light by the sun. And let's talk about the ultraviolet region. Here, humans need to wear the sunglasses, okay, in order to protect the tissue in your eyes, okay, because the energy is high, okay, if we watch the sunlight for a long time. And let's move further, the wavelength is shorter and shorter. It's called X-ray region, right? We use X-ray to see through what's going on in human body. For example, here is the hand of the human. And once we go further, we reach the final band of electromagnetic wave. It's known as gamma rays. Okay? The wavelength is very, very short. You can see the frequency band from 50 Hertz, 1 megahertz, 500 megahertz, okay, for radio, and 1 gigahertz for data communication, 10 gigahertz for satellite for microwave, 30 gigahertz for infrared, 600 terahertz, that's the frequency for the visible light, and 3 pentahertz for the ultraviolet, 300 pentahertz for X-ray, and 38 hertz is the frequency band for the gamma rays, which is very dangerous, right? Here, in both region, X-ray and gamma rays, it's extremely harmful to our human body. But once, if you take a look at this band in terms of wavelength, it's going to be 6,000 kilometers, okay, which is very, very far. 300 meter, 60 centimeter, and 1 foot, okay, till 3 centimeter, 10 millimeter, and the order of nanometer for the visible light, in 100 nanometer for the ultraviolet UV light, and very, very short, 1 nanometer, 10 picometer for the extreme band like X-ray and gamma rays. Okay, you may not often hear these two bands because they are very dangerous. You can see them only in a special occasion like at the hospital and so on. All right, that's the whole picture of the electromagnetic wave band, okay, in terms of frequency band. Now let's talk about the little bit an example for the computation of the wavelength and the frequency for the electromagnetic wave. Okay, it uses the same expression as I told, as you may have seen during our on-site class. We have C equal to lambda F, right? And the lambda is the wavelength, F is the frequency in terms of hertz, C is the speed of light. And in our level, we can, oh my God. Oh.โอ้เดี๋ยวแป๊บนึงนะครับผมซูมนั้นนะครับไม่ได้จ่ายเงินจะมีปัญหานะครับขออนุญาตแจ้งปริญญาตรีนิดนึงครับ All right, let's talk about let's talk about the computation in terms of C and lambda F. Okay. Here we consider the radio frequency band. It's AM, okay, amplitude modulation. The frequency of this band, okay, let's take a look at the figure first. What is AM, okay, amplitude modulation? You know that if you study, okay, in the future, if you go to electrical engineering department, okay, if you want to study electrical engineering, there is a branch of electrical engineering. It's called communication engineering, and amplitude modulation is a type of is a kind of modulation. Okay, we have frequency modulation, and it's known as FM, right? You may have ever heard FM, and yes, FM may deliver better sound quality. Okay, AM will deliver lower quality of the sound. How does the AM work? Okay, if this is the signal you want to transmit, let's say it's information bit 1 or bit 0 or bit whatever kind of whatever information you want to transmit, like it may be also a part of image or video or something like that. And here you have a carrier signal. Okay, it has a constant frequency. You can see that the length of the wave is constant. Okay, the power is not stretched. Okay, the width is the same for every powers, and okay, if you wanna make the AM signal, okay, it's in wireless communication or in communication engineering is known as modulation. Okay, but don't worry about, don't be panicked about the new word modulation. What is that? It's simply the multiplication between the original signal. Okay, any information you want to modulate, any information you want to transmit, that's the decided information, but you are allowed to transmit that information by using this frequency. Okay, it's like if you have ever seen the ancient radio. Okay, you just turn the knob, okay, the bottom in the radio to change your frequency. Yeah, that's knob or that rotation means you change or you look for a new frequency band. Okay, frequency for the amplitude modulation. You change the frequency so that you want to get or you want to hear something from a different radio station. And here is the desired information. It's only the multiplication between this one and this one. Okay, once you multiply the first row to the second row, you will get the third row. That's the outcome. Okay, and the radio station will transmit this one, okay, to the receiver. Okay, and at the receiver, they're gonna detect, okay, or decouple the information from this side. Once you know the frequency of the carrier signal. Okay, at the receiver, for example, you hold the radio at home. Okay, your radio will multiply or use some method to detect this waveform. Okay, to get back this waveform, and then you can know, this is the voice of A, B, C, D. Okay, from the radio station. Okay, that's the mechanism of amplitude modulation. The important thing for us is that carrier signal is the spatial value for different radio station, each radio station cannot use the same frequency. Otherwise, you will get the wrong information from different radio station. Okay, there will be interference among several radio stations. Each radio station has to use a unique frequency that is assigned by the government or the local government or in that province, in that area. Okay. Okay. For example, in this problem, they say the frequency band, the frequency of this radio station is 1.5 megahertz. So it means the frequency of the green one here is 1.5 megahertz. So what is the wavelength of this one? Okay, just use the ruler and to detect the length here. What is that? Okay. Oh my God, the zoom has closed. All right. Okay, that's the C equal to lambda F, the desired expression. Okay, you just move the F to the left hand side, right? Because this is a simple expression actually. Lambda is going to be the ratio between C divided by F, right? And you know that C is 3 times 10 to 8 meter per second. And F is the frequency, which is 1.5 megahertz. All right. Yeah, that will be the way you just substitute this one to this one, okay, to this position, and F like this to the denominator. But the important thing is that you need to where's the, here. The important thing is that you have to express this one in a spatial in a plane unit, right? In the typical unit, and that's 10 to 6 hertz. All right. Okay. Once you get this, then we are gonna see how the calculation is, right? You leave 3 times 10 to 8 for the high school level, and F as the frequency 1.5, 10 to 6, and you get almost 200, right? Because this is number 3 and this is 1.5, 200. Okay, 200 meter per cycle. Okay, it means the length here is 200 meter. All right, and many of you okay, many of you may have seen the AM, right? And let's move to the again the location of the AM band. Let's move to the location where the AM band is, right? AM or amplitude modulation is right here. Okay. The extreme band like gamma rays and X-ray is over there. The extreme band like gamma rays and X-ray are over there, and frequency for those two bands is very high, like it's 10 to 22 or something like that. AM is around here. It's a kind of low frequency electromagnetic wave. Okay, here is another picture of the whole electromagnetic band. And now we will talk about the next topic in this chapter. It's called polarization of electromagnetic waves, and here we're going to have more. I would say it's more calculation scenarios. As you have seen the diagram of electromagnetic wave, you can see that there are electric field and magnetic fields, right? And both fields have some fluctuation, or they oscillate in a single plane perpendicular to each other, and the traveling direction is perpendicular to both planes. The electric and magnetic field vibration in the EM wave can also oscillate in a different planes, and this is the situation we are going to see in this topic. Polarization is the ability of transverse wave to oscillate in more than one direction. Okay, the one you have seen is a simple case of electromagnetic wave. In ถ้าไม่รู้เรื่องตรงไหนนะครับโปรดขัดจังหวะผมทันทีนะครับเพื่อว่าคุณจะได้เข้าใจนะครับถามได้เลยนะครับ most common electromagnetic wave detectors could respond to electric forces on electron in materials, not the magnetic forces. So also the human eyes. Okay, we will depend mainly on the electric field. So we will not depend on magnetic field because many detectors are more sensitive to the electric field. And the direction of the polarization of an electromagnetic wave can be defined to be the direction of the electric field vector, not the magnetic field vector. And here are some types of polarization arrangements. They use mainly the electric field to represent the category of the EM wave. Okay, here you can see that there is fluctuation of the electric field in the vertical way, right? The fluctuation take place, okay, along the y-axis, going up and going down, right? That's what we have seen before, right? That's the typical way of the electromagnetic wave at the beginning. Once we combine the electric field with the magnetic field, you can see the magnetic field on the horizontal plane. Okay, the electric field is in the vertical plane. Okay, but the wave, the EM wave, the electromagnetic wave, is moving in this way. Okay, in this direction. This is the plane electromagnetic wave, and it is said to be linearly polarized. Linearly because it's only a vertical line here. When the transverse electric field wave is accompanied by in phase by magnetic field wave. Okay, because we have the magnetic field that has the same peak at the same time. Okay, that has the peak at the same time as the electric field. It's called in phase. Okay, when the electric field is lowered, the magnetic field is also lowest. Okay, when the electric field is highest, you get also highest amount of magnetic field. It's called in phase. Okay. Now let's talk about a more sophisticated type of arrangement of the electric field. Okay. It can happen that once at the starting point, we have the electric field in the horizontal plane like this, okay, horizontal plane. And once the wave goes by, the electric field goes by like 90 degrees, now the electric field becomes vertical, okay, and after that, it's going to be again by 90 degrees horizontal, okay. It change the alignment of the electric field like this, and horizontal and vertical, okay, like this all the time. And you can see that the electric field can happen in the horizontal plane and the vertical plane. And there is 90 degrees of the phase difference, okay. It means that we have two waves actually. The first wave is the wave that has the E field in horizontal way, horizontal plane. The second wave is the wave that has the electric field in the vertical way, okay. And once they combine to each other, you're going to see that the electric field gradually rotate once they move in this direction, okay. It's not just fixed vertically like this, okay, because it is composed of two electric fields actually. So the electric field actually the electric field that you can observe will rotate like this, okay, all the time, and that's the rotation. We call this one as we call such type of rotation of the E field as circularly polarized light, okay, and it consists of two perpendicular electromagnetic plane waves with equal amplitude. Once we have equal amplitude, it means the whole picture will be circle, okay, because the radius here is the radius in horizontal plane is the same as the radius in the vertical plane, okay, and there is 90 degree phase difference. In figure 24, the light illustrated is right hand circularly polarized, right hand, because if you stay here, if you are the person who observes here and you watch this E field from the bottom, you can see that the E field rotate like this, right? And yeah, it's if you lay your thumb direction, your remaining forefinger will be in the same direction as the rotation of the E field in this one. Okay, yeah, it's a little bit more complicated than the fixed polarization, okay, vertical or linear polarization like this. Okay, now let's move to the next case. If we have also two components of the E field, okay, one on the horizontal plane and another one on the vertical plane, but unfortunately, the height or the amplitude of the E field in the vertical plane is greater than the E field or the magnitude on the horizontal plane. And in this way, okay, of course, the E field will rotate, but rotate in a different way, because once it's vertical, the amplitude is greater than the amplitude in the horizontal way. All right, and finally, it's going to bring us the oval shape or elliptic shape, right? ภาษาไทยเรียกว่าวงรีครับ okay, and again, the E field will rotate like this, okay, along the propagation direction, and but they don't have the same amount of the magnitude, because the vertical one has greater E field than the horizontal electromagnetic field, electric field. All right, and the phase difference is still 90 degrees. We call this type as elliptically polarized, elliptical polarization. Okay, this is elliptical polarization. Elliptically polarized light consists of two perpendicular waves with unequal amplitude, and they are different in phase by 90 degrees. The illustration of the right-hand elliptical polarized light is in this figure. So in conclusion, we have linear polarization like this. Okay, the oscillation of the E field is only in the vertical line, but for the circular polarization, we have oscillation in both y-axis and x-axis, and fortunately, the magnitude of the horizontal plane is the same as the magnitude in the vertical plane. So finally, we get equal magnitude, and with the equal magnitude, we would, because the E field will rotate, right? We get the circle shape. And on the third figure, we have two components again of the E field, one on the horizontal plane, another one on the vertical plane. But unfortunately, on the vertical plane, we have higher or greater amount of the magnitude. And once the E field goes by, it's gonna rotate, right? Right-hand rotation. And what you can observe the E field by eye is that it will give you the elliptical shape or elliptic like this, okay? And these are three types of polarization that you may have seen during this class. Let's consider the transverse wave. It is linearly polarized in the y direction. It's gonna propagate like this. Okay. Okay, it has no rotation. Okay, the oscillation just takes place only along the y-axis. It's called linearly polarized in the y direction. And this one is also linear polarization, but the fluctuation or the oscillation take place in in the horizontal plane. Okay, ขออนุญาตครับผมลืมปิดไฟครับแสงสะท้อนนะครับขอปิดไฟแป๊บนึงครับ Okay. Yes. Let's talk about the device that is related to polarization, and we will bring you to a better situation, closer situation. An ideal polarizing filter, or simply called polarizer, will pass 100% of the incident light polarized in the direction of the filter polarizing axis, but block all lights that is polarized perpendicular to that axis. So it will allow every light that has the vertical polarizing axis. But when the light has the horizontal polarization, it will not be able to penetrate this filter or this polarizer. The most common polarizing filter for the light is material that is known in the trademark as Polaroid. I don't know whether you have seen this one, or, but once we complete a little bit the first chapter, I will ask your co-teacher so that we can have a chance to go to the laboratory the physics laboratory at the school, okay, so that you have chance to make some experiment. Okay, it's widely used for sunglasses. Okay, the Polaroid is used for sunglasses, and apart from that, it's also used in polarizing filter for camera lenses. I don't know whether you have. I don't know whether you are interested in photography or not, but polarizing filter is one of the filter for the camera professional man. All right, the professional cameraman. We have the ND filter, we have UV filter, but polarizing filter is also another type of filter for the professional cameraman. Okay, let's talk about the Polaroid in our subject. Polaroid that has the superscript TM because this is the trademark symbol. Polaroid filter will allow approximately 80% of the intensity of the light. Okay, the polar axis is parallel to a certain axis in the material. It's called polarizing axis, and it will allow 1% or less, or less than 1%. It depends on the quality of your wave. Okay, it depends on the quality of your wave. The polarization is perpendicular to these axes, actually. Okay, it's not like the ideal polarizing filter. Okay, ideal polarizing filter will allow 100% of the incident light intensity and 0% of the light in the perpendicular axis. But in reality, in the commercial product, or the filter will allow not 100%, okay, only 80% of the intensity of the wave that is parallel to the parallel axis of the filter, and will cannot completely obstruct the wave that is perpendicular to the filter axis or polarizing filter axis. Okay, it will allow, it will let 1%. Okay, it will permit 1% of the wave to propagate through the vertical polarizing axis of that filter. Okay, this is the filter in reality, not the ideal one. Okay, ก็บทนี้นะครับก็จะเป็นเรื่องเกี่ยวกับการศึกษานะครับว่าแสงเดินทางผ่านฟิลเตอร์นะครับหรือภาษาอันนี้เรียกว่า polarizer นะครับก็คือใช้สำหรับนะครับดูว่าบังคับให้แสงวิ่งไปเฉพาะแนวตั้งเนี่ยนะครับมันก็จะมีแสงบางส่วนถูกลดความเข้มลงครับพอลดความเข้มลงนะครับเวลาฉากรับเราก็จะได้รับแสงที่น้อยกว่าเดิมก็คือมันก็จะมืดลงนะครับส่วนมืดลงมากน้อยขนาดไหนมีความสัมพันธ์อย่างไรเดี๋ยวดูในสูตรนะครับ Okay, let's move to the next page. Here is the explanation in a better way so that you can understand from the figure. Okay, in the light there could be many orientation of the E field. Okay, we are interested in only the electric field because this is the field that human use several devices to detect. Okay, it's very hard to detect the E field, the magnetic field, but for the E field, human can detect those access easily. Okay, not difficult. So here is the original light that has several orientations of the E field, and one is propagates through this เดี๋ยวนะครับผมต้องจบคุณกี่โมงอะE2 no SCI wait SCI
330205. What time is that? Where's okay? 14, right? Oh, still long. Okay, 1410, right? Okay, and here is the Polaroid filter. It will allow the electric wave or the light electromagnetic wave that has the polarization axis in this orientation. Okay, it's called vertical polarizing axis only. So the light that has polarizing axis in a different orientation, like this one or this one in horizontal plane, will not be allowed, okay, to pass through this filter. Okay, only the light that has vertical polarizing axis will be able to transmit through this filter. Okay, but the percent is not 100, it's like 80% according to reality. Maybe in your generation, you may be able to build up a filter that can allow 100% of the light. Okay, but at the moment it's solely 80%. Okay, polarization filter, namely Polaroid, produces polarized light. Okay, it will block every light component that has the orientation apart from these. Okay, we will talk about the intensity, but before we talk about the intensity calculation, you need to know some areas in physics. Radiometry is the detection and measurement of optical radiation at any wavelength. It's based simply on the physical measurement. Okay, this is the subject or research area many people are interested in. Okay, and in the radiometry, there is a word which is called irradiance. Okay, irradiance, you may call it. Irradiance is the radiant flux or the power received by a surface per unit area. Okay, it's called irradiance. And the SI unit of the irradiance is watt per square meter, like this. Irradiance is often called intensity, but this term is avoided in radiometry, where such usage leads to confusion and radiant intensity. So we will use in astrophysics, the people call irradiance as radiant flux, but for us, we will call irradiance somehow as intensity. Let's talk about this experiment. Once your light has several orientations of the E field of the electric field, you place the polarizer with polarizing axis adjustable. Okay, you can adjust the polarizing axis through this knob to just rotate it. Okay, for example, if you let the light, if you move the polarizing axis in this way, okay, only the light that has polarizing axis corresponding to this line will be able to transmit through this filter, and this amount of light will be finally collected to reach the any measurement device. Okay, transmitted lights linearly polarized parallel to the polarizing axis. Okay, the intensity of the transmitted light is the same as And same for our orientation of the polarizing filter. Whether you leave the blue knob here or whether up here or right there, you will get the same amount of light intensity. And for an ideal polarizing filter, the transmitted intensity is half the incident intensity. So the intensity after the incident light will be only 50%, okay, of power from the original source of the light. Let's talk about phi, which is the angle that we rotate or shift the polarization axis a little bit from the vertical line. Once you have the light in any polarization orientation, okay, this represents the E field. And once you have the knob like this, okay, only the light that has the polarizing axis like this, okay, will be transmitted through the first polarizing filter. And let's talk about what's going on further. If you have another polarizing filter, you can lay, okay, and please make sure that the center of the first one and the second one should be lie in the same way, and should be also at the center of this pipe, and we use photocell to detect how much energy we get. All right. Yes. Once you rotate the knob like this, only the wave that has direction like if you here could be transmitted. And what's going on? We can have two components because this is the maximal angle deviation, which is phi, right? We can decompose this vector to the vertical line and decompose this vector to the horizontal line. All right. And once you have another filter, can you guess which component could be transmitted through this polarizing filter? Of course, the polarizing axis is vertical, so only the wave that has the E field in the vertical wave will be able to transmit through this filter. And finally, we get only E cosine. Okay, and this light will hit the sensor at the end of this tunnel. Okay, linearly polarized light from the first polarizer can be resolved in two components, E parallel and E perpendicular, right? But E perpendicular is no meaningful because it's gonna be perpendicular to the vertical line. Okay, this is the effect of passing unpolarized light through two polarizer. And let's talk about what's going on here in this experiment. What is the final intensity we could get from this experiment? And this question has been raised by someone, and they developed an expression for that. When immediately polarized light strike a polarizing filter and its axis at angle phi to the direction of polarization, the intensity of the transmitted signal will be equal to I max, okay, I max the maximum value of intensity, and cosine square. Okay, cosine square in means the box here. Okay, cosine square means the deviation once you have the orientation by phi, okay, from the vertical line. Imax is the maximum intensity of the light. Okay, transmitted at phi equals 0, and the unit is watt per square meter. Right, it's spatial ratio for us. I is not the current. I is the amount of transmitted at angle phi. Okay, this I is not electric current. Is intensity in physics. This relation has been discovered by Malus. Okay, Malus law. The relationship is discovered by experimentally by this person. Who, any of you who can pronounce this word? มีไหมครับใครอ่านออกเสียงได้ไหมครับนี่เป็นภาษาฝรั่งเศสผมไม่เคยครับ Maybe we call Louis Malus, okay, and it's simply known as Malus law. Okay. Before we go to the example, may I go to the toilet for a while? ขออนุญาตเข้าห้องน้ำแป๊บนึงครับ Okay, we arrive at I think it's the third example for calculation, right? Yeah, please keep in mind that the midterm exam or something that will be 100% based on the example here, okay, or the difference will be only the number. Okay, if we have a narrow beam of unpolarized light, okay, with the intensity of I0, the Malus law is somehow Imax time cosine square and angle phi, right? Imax is maximum intensity. Okay, when we move the polarizing axis to be 0 at vertical moment, and the unit of intensity is watt per square meter. I is the intensity at any angle. Okay, if you rotate this one, okay, you will get the intensity after that, depending on the angle phi. Okay, it's discovered by Etienne Louis Marus, right, in 1809. 1809. Here we start with the intensity of I0 at the beginning. It is directed to a pair of polarizing sunglasses. Okay, so we have two pieces of the polarizing filters, right? If the angle between polarizing axes of the two lenses is 30 degrees. Okay, let's see. What intensity do you expect to find after the beam passes through the first lens and after it passes through the second lens? Okay, I think there should be no adjective through. It's maybe the wrong one. Okay. So let's, if you don't understand completely what's going on from the text, you may take a look at the figure here. Okay, they have also provided the figure. First of all, you have unpolarized light. Okay, it has different orientation of the electric field, as you know before. And for the first lens, okay, this is your eyeglasses. The first lens is arranged in such a way that the polarizing axis is 30 degree deviated from the vertical line. Okay, เลนส์ชิ้นแรกครับถูกจัดตั้งไว้อย่างนี้แล้วก็ให้มีแกนของการ polarization ครับแกนของการ polarization ก็คือแกนที่ยอมให้คลื่นเหล็กไฟฟ้าที่มีสนาม E นะครับสนามไฟฟ้าเนี่ยเฉพาะแนวนี้เท่านั้นที่ผ่านได้ครับโอเคไหม and it is tilted by 30 degree. So of course only the light that has the E field that is tilted like this or deviated like this will take place, okay, will happen after the first lens. And once it propagates further, it's obstructed by the second lens, but the orientation of the polarizing axis is exactly vertical, okay, in the same way as the vertical axis like this. So the outcome will be the wavelength that has the E field in the vertical orientation like this. Okay, this is the first lens, this is the second lens. We could do it by using the Malus law. But anyway, after the first lens, the intensity will be reduced. Okay, the intensity will be reduced by 50%. So the intensity that you can observe after the first lens will be 50%, or it's 1/2 in terms of mathematics. Okay, you will get half of the intensity after the first lens, and once you pass it through the second lens, okay, if you pass it through this, you will get the intensity E2, and I2 could be computed from the Malus law. Okay, Malus law here. Imax and cosine square theta. And as you know, your Imax is I1, right? Your Imax is I1, so it's 1/2 I0. Okay, and we substitute the amount of angle that is deviated 30 degrees into the expression by malus, and you could see that I2 is I1, right, times cosine square and cosine, and the tilted angle is tilting angle is 30 degrees. And as you know, cosine of 30 is square root 3 divided by 2, right? But we need to have to make the square because it's power of 2. I1 will be the result from the previous or the former expression, right, after the first one. The intensity is reduced 1/2 and is propagated through the second lens, okay, that has polarizing axis in the vertical arrangement like this. Once you substitute I1 by I0/2 in cosine square square root 3/2, and this is square, this is 3/4, and 1/2 is going to be 3/8. Okay, so the result will be finally 3/8 of I0. Okay, please note that here we have a light that is very but it has so much energy because it has several orientation of polarization. For the first lens, the polarizing filter will reduce the intensity of the unpolarized light to be only half of that. So it's intensity of this one, okay, divided by 2. That will be the result after the first lens. But you cannot say the intensity here will be half of this one because this is already the polarized light, okay? And you have to use the malus law. It depends on the orientation of the angle difference between the polarizing axis and the incident light. โอเคนะครับภาษาไทยก็คือถ้าคุณมีแสงที่มันไม่ได้ polarized ก็คือมันมีแกนของสนาม E หมุนทุกทิศทุกทางมานะครับก็คือมันความเข้มสูงเนาะถ้าหลักการก็คือว่าถ้าเราเอาเลนส์ polarized นะครับก็คือตัวฟิลเตอร์เนี่ยเลนส์สีดำที่เป็นกันแสงนะครับกันแสงคำว่ากันแสงก็คือบล็อกแกน polarized นะครับ polarizing axis อันอื่นทั้งหมดนะครับแล้วก็ยอมให้แสงที่มีแกน polarized ตามเลนส์นั้นเท่านั้นครับที่ไปได้แต่เนื่องจากอันนี้เขาไปเอียง30องศานะครับแสงที่ไปได้ก็คือต้องมีสนาม E ที่เอียงมา30องศาด้วยนะครับส่วนแกนอื่นของสนาม E ของแสงครับถูกบล็อกถูกกันไว้ด้วยเลนส์ชิ้นที่1แล้วนะครับโอเคนะครับคุณไม่สามารถบอกได้ว่าอันเนี้ยมันจะต้องมีความเข้มเป็นครึ่งหนึ่งของอันนี้ไม่ใช่นะคือถ้าแสงมามันไม่มีโพลาไรซ์มันมีทุกแกนโอเคคุณตอบได้ว่าอันเนี้ยจะต้องมีความเข้มเท่ากับครึ่งหนึ่งของอันนี้แต่อันนี้มันเป็นแสงที่โพลาไรซ์แล้วนะครับก็คือจัดวางกองมาแล้วเอาเฉพาะสนาม E ที่มันเองอย่างนี้30องศาเท่านั้นครับดังนั้นจะตอบว่าเป็นครึ่งหนึ่งของอันนี้ไม่ได้คุณต้องใช้สูตร Malus law ตรงนี้นะครับโอเคมา Imax cosine square theta โอเคI put the wrong live stream YouTube channel. Okay, yeah, that's the example in the calculation of the polarization. Okay, the light is regarded as having a dual nature. You can see this word later because it can be also electromagnetic wave. It can be also like a particle. Okay, and that's the Broad wavelength and so on. But we will not talk about that in this chapter. The light in classical magnetic wave theory, we would say that the light can propagate, and there is also interference effect. The photoelectric effect is the experiment for determining how the atom behave. Okay, that's what you may see in chapter 6. Other interaction of the light with matter are best explained by assuming that the light is a particle. Okay, once the light has some interaction with other phenomenon, other matter, we would consider the light as a particle. Okay, and that's why they say light has dual nature, has two natures. The first one is the same as the classical electromagnetic wave theory. It's only a magnetic wave, but when it hits or it does some interaction, it interacts with some matter or particle, we're going to see that the light is a particle. So it can be either electromagnetic wave and particle too. Okay, that's a special thing for the light. The light, because this is the result of the modern physics or middle age physics. Okay, the light has a number of physical properties, some associated with the wave and other with particles. So that's the dual nature of the light. Okay, คุณต้องการให้ผมไปต่อถึง14-20นะครับหรือว่าจะขอจบที่14-10เพราะว่าระหว่างสอนผมก็จัดการเรื่องปริญญาตรีด้วยนะครับเขาสอบตอนบ่ายโมงครับซึ่งหลังจากเราเริ่มเรียนได้สักประมาณ20นาทีครับเพราะเขานัดสอบกันวันนี้นะครับก็เสียเวลาไปกับเขาด้วยถ้าคิดว่าผมเสียเวลากับการจัดการปริญญาตรีด้วยผมก็ใช้10นาทีนี้เพื่อชดเชยให้นะครับโอเคหรือว่าถ้าคุณอยากเลิกก่อนเลยหรือว่าอย่างไรแล้วแต่คุณแจ้งผมมาทางซูมก็ได้นะครับ Is there any information นะครับพวกคนที่พิมพ์ชื่อมาครับต้องการให้ผมต่อไปเลยไหมครับเพื่อชนเวลาของ605เลยหรือว่าจะเลิกแล้วแต่จริงๆผมก็เสียเวลานิดนึง
เลิกได้
อะไรนะครับ
เลิก
เดี๋ยวผมได้ยินคุณไม่ชัดครับเนื่องจากเทคโนโลยีเสียง
เลิก
โอเคครับ so we are gonna quit our lecture today at the moment see you on Friday สวัสดีครับบ๊ายบายครับโปรดอย่าลืมพิมพ์ชื่อนะครับ
สวัสดีครับ
สวัสดีครับถ้ามีคำถามใดก็ถามได้เลยนะครับ